Hello, everyone, and welcome to this exciting journey into the world of quantum computing titled Exploring the Quantum Frontier, the Intersection of Physics and Computing. My name is Mirko Peters, and I'll be your guide as we delve into the fascinating convergence of cutting-edge technology and fundamental physics. Whether you're here out of curiosity or to deepen your understanding of this transformative field, you've come to the right place. Before we begin, make sure to hit the subscribe button and follow us on LinkedIn for more educational content on data science, quantum computing, and the latest tech insights. Let's get started. Let's dive into the introduction to quantum computing. First, let's talk about fundamental concepts. At the core of quantum computing is the qubit, which is capable of representing not just 0 or 1, but both simultaneously, thanks to a phenomenon called superposition. Imagine the power. A 100-qubit computer can represent an astronomical number of states, around 1030. Then there's entanglement, another cornerstone. This allows qubits to influence one another instantaneously, regardless of distance, amplifying their computational capabilities. Now, why is this revolutionary? It's the advantages over classical computing. Quantum systems are incredibly fast and efficient. They can solve problems like optimization, molecular modeling, or cryptography in moments, tasks that would take classical systems years to compute. This marks a paradigm shift in how we process information. Onward to explore more. Next, let's explore the historical impact of quantum theory. Foundation of modern physics. Quantum theory took center stage in the early 20th century with Max Planck's groundbreaking concept of quanta in 1900. This revolutionized our understanding of energy and matter, laying the groundwork for quantum mechanics, a field that probes phenomena at the atomic and subatomic levels. Technological innovations. Quantum principles have birthed transformative technologies. Think about transistors and lasers, cornerstones of modern computing and telecommunications. Even the miniaturization and efficiency of electronic devices in the semiconductor industry owe their progress to quantum mechanics. Philosophical and scientific paradigm shift. This wasn't just a scientific revolution, but a philosophical one too. Ideas like superposition and entanglement shattered classical notions of determinism. Niels Bohr's Copenhagen interpretation went further, asserting that particles don't possess definite properties until observed, redefining how we think about reality. Quantum theory is truly the bedrock of both technological innovation and scientific exploration. Registers and memory cells. Registers are specialized components that hold multiple bits, commonly 32 or 64 bits. Similarly, memory cells store classical bits, enabling data storage and retrieval. Limitations of classical representation. Classical bits, however, are limited to just 0 or 1. This constrains their ability to handle complex problems. Contrast this with quantum computing, where qubits leverage superpositions, enabling vastly more computational power. This distinction between classical and quantum systems marks a significant leap in data processing. Let's dive into the topic of binary data representation. Fundamental concepts. Binary data is the bedrock of classical computing. Each bit represents a state, either 0 for off or false, or 1 for on or true. This system processes and transmits all data as sequences of these bits. Logic gates and operations. Logic gates like AND, NOT, and copy manipulate bits to perform operations. They are the essential building blocks for executing mathematical functions and powering computational tasks. On this slide, let's discuss the role of atoms in modern computing, foundation of quantum mechanics. Atoms composed of nuclei and electrons are governed by the principles of quantum mechanics. These laws dictate their interactions and behaviors, making this understanding essential for advancements in modern computing technologies, especially in the semiconductor industry. Transistors and integrated circuits, solid-state physics, and band theory paved the way for the development of transistors and integrated circuits, the core components of classical computers. These innovations have revolutionized technology, enabling miniaturization and enhanced performance. Quantum computing and qubits. In quantum computing, atoms act as the basis for qubits, the fundamental unit of quantum information. Unlike classical bits, qubits can exist in superposition, enabling exponential computational power. For instance, a system with just 100 qubits can represent 1030 states, exemplifying the vast potential of atomic scale manipulation in computation. This interconnection between atomic principles and modern computing truly showcases the impact of physics on technology. Let's dive into the advancements in the semiconductor industry. Evolution of transistor technology. Transistors have significantly evolved, becoming increasingly miniaturized. Modern chips can now be manufactured at sizes as small as 5 nanometers, allowing for a higher density of transistors and enabling powerful and efficient computing capabilities. Impact of quantum mechanics. The principles of quantum mechanics, such as solid-state physics, play a crucial role in the development of transistors and integrated circuits. However, as transistors approach atomic scales, phenomena like the tunnel effect introduce challenges, potentially affecting reliability and performance. Moore's law and its implications. Gordon Moore's famous prediction states that the number of transistors on an integrated circuit doubles approximately every 2 years. This trend has led to processors such as the Intel Core i3, i5, i7 series containing billions of transistors, up to 1.75 billion in some models, packed into compact dies. Challenges in scaling down. As we continue to scale down semiconductor technology, new limitations arise. At the nanoscale, electrons can escape from their intended pathways due to quantum effects, creating malfunctions in chips. This highlights the need for innovative solutions in semiconductor design to overcome these challenges. Now, let's take a moment to reflect. How do you think advancements in semiconductor technologies will shape the future of computing? Drop your thoughts in the comments below. Now, let's explore the technological innovations driven by quantum physics. Quantum computing advancements. Quantum computers harness the principles of superposition and entanglement, allowing qubits to represent vast amounts of information simultaneously. For example, a 100-qubit computer can represent approximately 1030 states, offering capabilities far beyond classical systems. Breakthrough algorithms like Shor's algorithm for factoring large numbers and Grover's algorithm for database searches showcase the immense potential of quantum computing in tackling problems deemed impractical for traditional computers. Quantum cloud services, platforms such as Tsinghua University's Quantum in the Cloud and Quantum Inspire by QTech grant users access to quantum resources. These platforms enable experimentation and development without requiring dedicated quantum hardware, promoting a hybrid model where classical systems handle general tasks, while quantum systems address specific computational challenges. Applications in various fields. Quantum computing is revolutionizing industries by solving complex problems in cybersecurity, drug development, and supply chain optimization. Looking ahead, the integration of quantum technologies is poised to transform fields reliant on intricate data processing, paving the way for groundbreaking innovations and solutions. Classical Boolean logic forms the backbone of traditional computing systems. In classical computing, binary variables, which can take on the values of 0 or 1, are used to perform logical operations. This foundational framework enables computers to execute algorithms through basic operations such as AND, OR, and NOT gates. It's this logic that has powered the growth of classical computing for decades. However, with the advent of quantum computing, a seamless integration with classical Boolean logic has emerged. While quantum systems process information in fundamentally different ways, leveraging superpositions and entanglement, they still utilize Boolean logic for many operations. This hybrid approach creates a synergy that allows general tasks to be handled effectively by classical systems, while complex computations are taken up by quantum methodologies. Ultimately, this integration ensures a smooth transition between the classical and quantum worlds, enhancing computational efficiency while leveraging the strengths of both paradigms. Now, let's explore the distinction between qubits and classical bits. the fundamental units of quantum and classical computing. Starting with classical bits, these are the basic units of data in traditional computing. Classical bits can only exist in one of two states, either 0 or 1. This deterministic behavior forms the basis for all classical computing operations. However, this structure limits their computational power. For instance, a classical system with 50 bits can only represent one of over a quadrillion possible configurations at a given moment, restricting its ability to handle complex calculations effectively. In contrast, qubits are the building blocks of quantum computing and are far more versatile. A qubit can exist in multiple states simultaneously due to the phenomenon of superposition. It can represent 0, 1, or even a combination of both states at the same time. This unique property enables quantum systems to process massive amounts of data in parallel. For example, a 5-qubit system can represent 32 states simultaneously, while a 100-qubit system can represent an astonishing 10 to the power of 30 states. This exponential scalability drastically enhances computational power, allowing quantum computers to solve problems beyond the capabilities of classical systems. By leveraging these advanced properties, qubits pave the way for breakthroughs in fields like cryptography, optimization, and complex simulations, marking a paradigm shift in how we approach computation. On this slide, we delve deeper into the concept of quantum states and their fascinating properties. First, let's start with the definition of quantum states. Quantum states represent the knowledge or the configuration of a quantum system. Governed by the principles of quantum mechanics, these states can exist in multiple configurations simultaneously, a feature that enables quantum systems to perform complex computations far beyond classical systems. Next, we have superposition and its implications. Superposition allows quantum states, or qubits, to exist in a combination of 0 and 1 at the same time. For example, with 2 qubits, we can represent 4 possible states, 0, 0, 0, 1, 10, and 11 simultaneously. This property significantly enhances the parallel processing power of quantum computers, enabling them to solve problems that would be infeasible with classical systems. Finally, let's explore entanglement and correlation. Entanglement is a unique phenomenon where 2 or more qubits become interconnected, such that the state of one qubit instantaneously influences the state of another, regardless of the physical distance between them. This property allows for complex relationships and computations that are simply unattainable with classical systems. Together, these concepts, superposition, entanglement, and quantum states, form the backbone of quantum computing's transformative potential. Now, let's explore one of the core principles of quantum mechanics, superposition, and its critical role in enabling parallel processing in quantum systems. First, let's begin with understanding superposition. Superposition is a fundamental principle of quantum mechanics, allowing quantum bits, or qubits, to exist in multiple states simultaneously. Unlike classical bits, which can only be 0 or 1 at any given time, a qubit can represent 0, 1, or both at the same time. This unique property enables quantum computers to process a vast amount of information concurrently. For example, a quantum system with just 5 qubits can represent 32 different states simultaneously. That's 252, 5, or 32 states, showcasing how quantum systems exponentially grow in computational power as more qubits are added. This unique property enables quantum computers to process a vast amount of information concurrently. For example, a quantum system with just 5 qubits can represent 32 different states simultaneously. That's 252, 5, or 32 states, showcasing how quantum systems exponentially grow in computational power as more qubits are added. Next, we look at the implications for parallel processing. By leveraging superposition, quantum computers gain significant advantages in processing power. For instance, a 2-qubit system can represent all 4 binary configurations, 00, 01, 10, and 11, at the same time. Imagine the potential for simultaneous computations that classical computers would require multiple machines to achieve. As we scale up the number of qubits, this parallel processing potential grows exponentially. A quantum computer with 100 qubits can represent approximately 10 to 3010, 30 states. This capability makes it possible to solve complex problems much faster than traditional systems, which can only process one state at a time. In summary, superposition isn't just a fascinating scientific concept. It's the engine that powers the exponential capabilities of quantum computing. Let's delve into the concept of hybrid computing models, which blend classical and quantum systems to achieve unprecedented computational capabilities. First, we have the integration of classical and quantum systems. Classical computers will continue to play a critical role alongside quantum systems, handling general-purpose tasks efficiently. Quantum computers, on the other hand, will tackle specific problems that leverage their unique abilities, such as superposition and entanglement. Next, we look at parallel processing capabilities. Quantum computers excel at handling multiple states simultaneously. For instance, a 10-qubit quantum system can represent over 1,000 states, while a 100-qubit system can represent approximately 1030 or 1030 states. This immense parallelism enables quantum systems to solve problems that are computationally prohibitive for classical systems. Moving forward, technological collaboration is key to the success of hybrid models. By combining the strengths of both classical and quantum technologies, we can optimize tasks. Classical systems manage routine operations, while quantum computers focus on solving highly complex problems. Lastly, we address the future prospects and challenges. As quantum technology matures, hybrid computing is expected to revolutionize fields like cybersecurity and drug development. However, significant challenges remain, including the need for specialized environments, such as extremely low temperatures and high vacuum conditions, to maintain qubit functionality. In conclusion, hybrid models represent a bridge to the future, blending the reliability of classical computing with the groundbreaking potential of quantum technologies. Looking ahead, let's explore the future of quantum computing. First, we have advancements in quantum algorithms. Breakthroughs such as Shor's algorithm and Grover's algorithm highlight the potential of quantum computing. These algorithms excel in solving complex problems such as factoring large numbers and searching unstructured databases, tasks that classical computers struggle with. They showcase the power of quantum systems in leveraging superposition and entanglement to surpass classical methods. Second, is the integration with classical systems. Quantum computers are not expected to replace classical ones. Instead, they will work alongside them, handling specific tasks optimized for quantum mechanics, while classical systems manage general-purpose computing needs. This hybrid model allows for a more efficient use of computational resources, optimizing problem-solving across industries. Finally, we address the challenges and opportunities ahead. Practical quantum computing faces significant hurdles. These include the need for error correction and maintaining qubit stability at temperatures near absolute zero, approximately 15 millikelvin. Despite these challenges, the opportunities are immense. Fields like cybersecurity, drug development, and complex simulations stand to benefit greatly. Experts estimate that achieving a truly universal quantum computer might require around 1 million qubits. In conclusion, while the path to fully realizing quantum computing's potential is challenging, the transformative possibilities it holds promise a future of unparalleled innovation and efficiency. Let's delve into traditional logic gates, a foundational concept in computing. First, we have the fundamental components of computing. Logic gates form the building blocks of electronic circuits. These circuits are created by connecting multiple transistors, enabling computers to perform essential arithmetic operations like addition, subtraction, and multiplication. Each logic gate processes binary bits represented as 0 off or 1 on to manipulate and transmit information through electronic systems. Next, we examine the types of logic gates. Basic gates such as AND, OR, and NOT are the most common. For example, an OR gate outputs a 1 if at least one of its inputs is 1. A NOT gate inverts the input state. Additionally, more advanced configurations like flip-flops and registers combine these basic gates. These setups allow for the storage and manipulation of multiple bits, often in parallel arrangements such as 32-bit or 64-bit registers. These logic gates form the backbone of classical computing, driving every calculation and operation in modern electronics. Now let's explore quantum data and qubits, the foundation of quantum computing. First, we start with understanding qubits. Qubits are the fundamental units of quantum data, capable of representing 0, 1, or both simultaneously due to the principle of superposition. This unique property sets them apart from classical bits, which can exist only in one state at any given time, either 0 or 1. Second, we dive into superposition and its implications. Superposition allows a small number of qubits to represent a vast array of states simultaneously. For instance, just 5 qubits can represent 32 different states, or 2 to the power of 5 at the same time. This enables quantum computers to perform multiple calculations in parallel, significantly enhancing computational power and efficiency. Finally, let's discuss entanglement, a key feature. Entanglement enables qubits to become interconnected so that the state of one qubit instantaneously affects the state of another, regardless of the distance between them. This phenomenon enhances the complexity and capability of quantum systems, making it possible to solve problems that classical computers cannot tackle. These principles of qubits, superposition, and entanglement form the backbone of quantum computational advantage. Moving forward, let's dive into electromagnetic waves and quantum calculations. First, electromagnetic waves. These are defined as radiation that propagates through space, characterized by oscillating electric and magnetic fields. These waves include phenomena like light and radio waves and are foundational to both classical and quantum physics. Second, wave-particle duality. This concept highlights that electromagnetic radiation exhibits both wave-like and particle-like properties. This duality is central to quantum mechanics and helps explain phenomena such as interference and diffraction, as observed in light experiments. Third, we explore quantum calculations in electromagnetic contexts. Quantum mechanics enables the representation of electromagnetic states using complex numbers and vectors in high-dimensional spaces. This framework allows efficient execution of operations like Fourier transforms, which are crucial for analyzing wave behavior. Finally, we discuss the applications of quantum mechanics in electromagnetic theory. These calculations enhance the modeling of complex systems, such as atomic behavior under electromagnetic influence. This understanding is critical for advancements in areas like quantum optics and materials science, where interactions at the quantum level drive innovation. This slide showcases how quantum mechanics integrates with electromagnetic theory to deepen our understanding and enable technological progress. Now, let's delve into the fundamentals of logic gates, a cornerstone in modern computing. First, the definition and functionality. Logic gates are fundamental components in computing that perform basic operations based on binary inputs, zeros and ones. They are built using transistors, which function as switches, controlling the flow of electrical signals. This setup enables the execution of essential arithmetic operations such as addition, subtraction, and multiplication. Second, the types of logic gates. These include the AND gate, which outputs 1 only if both inputs are 1. Otherwise, it outputs 0. The OR gate, which outputs 1 if at least one input is 1. It outputs 0 only if both inputs are 0. The NOT gate, which inverts the input, outputting 1 if the input is 0, and vice versa. These gates can be combined to create more complex circuits capable of performing a wide range of computations. Lastly, let's explore transistor integration and evolution. Modern microprocessors house billions of transistors on a single silicon chip, showcasing significant advancements in miniaturization and efficiency. The evolution from early vacuum tubes to today's integrated circuits exemplifies the rapid progress in computing technology, enabling faster and more powerful processing capabilities. Understanding logic gates is pivotal for grasping the principles of both classical and quantum computing systems. Moore's law has been a cornerstone of technological innovation, predicting the doubling of transistor density in integrated circuits approximately every 2 years. This exponential growth has led to tremendous advancements in computational power and efficiency. Point 1. Transistor density growth. As a result, modern processors are now produced at nanometer scales as small as 5 nanometer, enabling chips like the Intel Core series to feature billions of transistors. Point 2. Performance enhancements. This increase in transistor density significantly boosts performance, allowing processors to handle more operations simultaneously and at higher speeds. For example, processors exceeding 3 GHz in frequency can manage complex tasks with greater efficiency. Point 3. Challenges of miniaturization. However, the continued reduction in transistor size introduces challenges. At nanoscale levels, quantum phenomena like the tunnel effect can cause malfunctions, pushing us to the physical limits of traditional digital computing. Point 4. The future of digital computing. These challenges highlight the potential need for a paradigm shift towards alternative technologies, such as quantum computing. Exploring quantum mechanics at the nanoscale offers new avenues for innovation beyond the constraints of Moore's law. What are your thoughts on how we can bridge the gap between current technologies and future computational needs? This slide explores two of the most transformative theories in physics that have reshaped our understanding of the universe: the theory of relativity and quantum mechanics. Point 1. The theory of relativity, developed by Albert Einstein. This groundbreaking theory integrates space, time, and gravity into a single continuum, challenging classical Newtonian physics. It posits that the laws of physics are universal, irrespective of an observer's motion. Concepts like time dilation and gravitational waves are among its pivotal insights. Point 2. Quantum mechanics at the atomic and subatomic levels. Quantum mechanics reveals the duality of particles and waves. Through phenomena such as wave-particle duality and Heisenberg's uncertainty principle, it challenges the deterministic view of nature, emphasizing probabilities over certainties. Point 3. Impact on modern science. These theories have driven incredible advancements in technology, from atomic clocks to lasers and MRI machines, illustrating their profound influence on scientific and technological progress. Moreover, the unified understanding of matter and energy has paved the way for innovations in quantum computing and other cutting-edge fields. How do these revolutionary theories inspire your perception of the universe? Here we introduces the fascinating concept of the many worlds interpretation of quantum theory. Point 1. Overview of many worlds theory. This theory proposes that every quantum event results in a branching of the universe where all possible outcomes exist simultaneously in parallel realities. Instead of collapsing into one observable state, quantum possibilities coexist in a multiverse. Point 2. Key proponents. Visionary physicists like Stephen Hawking and Richard Feynman have significantly contributed to the understanding and acceptance of this interpretation, enriching our grasp of quantum mechanics. Point 3. Implications for quantum mechanics. This perspective challenges the classical idea of a singular, observable reality, suggesting that quantum events maintain an array of possibilities, reframing how we understand interactions at the quantum level. Point 4. Comparison with classical physics. Unlike classical physics, where determinism reigns, the many worlds theory highlights the counterintuitive role of observation, fundamentally shifting how outcomes are perceived in quantum phenomena. Point 5. Philosophical considerations. Beyond physics, this theory raises profound questions about the nature of reality, the role of the observer, and even free will, inviting deeper exploration into the philosophical dimensions of quantum mechanics. Okay, back to the real world. Here's the conclusion. Quantum computing has the transformative potential to revolutionize industries, from cybersecurity to drug development, by harnessing the unique properties of qubits. However, significant challenges lie ahead, including stabilizing qubits and managing noise, which require sustained research and investment. As advancements in hybrid computing models and quantum cloud services continue, we are entering a future where the integration of classical and quantum systems will redefine computational capabilities. Thank you for exploring this fascinating frontier with us. If you found this presentation insightful, don't forget to hit the like button, share it with your peers, and leave a comment below. And of course, follow us for more exciting content on cutting-edge data science and quantum technology.